Hello, everybody. Welcome to the Rockin Pop-Up. My name is Marisa Gomez. I'm the Public Programs Manager at the Santa Cruz Museum of Natural History, and I am really excited to go back in time with you all today. We are going to go back to a time when things were much colder. We're going to visit some past ice ages for the Earth, and that is why I'm all bundled up for us to do that. But before we go back in time, we thought that it might be fun to look forward in time a little bit, because this is actually going to be the final Rockin Pop-Up of the year 2020. If you can believe that. We have done so many of these. I don't even know how many we've done of these. So many. And we are really looking forward to continuing this on in 2021. But, you know, there's a lot up in the air. Who knows what 2021 is going to be like. So I'm going to invite in our Geology Gents, Gavin and Graham, and I want to ask you all a question. So, hello, Gavin.
Hey,
hello,
Marisa.
Graham.
Hey, Marisa.
Hi. So yeah, I'm curious what you both are looking forward to for 2021. Maybe like, what's your New Year's resolution, but in terms of geology, what are you hoping to maybe accomplish in your geologic endeavors? Or maybe like, are you hoping to be able to go visit some rocks somewhere? What do you got? Let's start with Gavin. What do you think?
It's a great question, Marisa. I think that just like many other scientists, my resolutions are always to write a paper. So I have a paper that I'm working on about Antarctica, actually, very close in topic to what we're talking about today. So a resolution is to get that out. Looking forward to working on some other Antarctic rocks. And in terms of places to visit, I just hope I get to visit anywhere besides Santa Cruz.
Yeah, I hear ya. Graham, what about you?
Yeah, so my 2021 geologic plans are looking at the other pole. I've just started collecting some data, making some measurements on some rocks that formed during the last ice age, way up in Canada. And I've just gotten my first few sniffs of these rocks, and I'm really excited to keep collecting more data on them and see what story they have to tell.
Whoa, you're going to the North Pole?
I wish I were actually going there. These rocks are back from a long time ago, so I'm just studying them now, but maybe someday.
Maybe someday. That sounds very exciting. And for everyone joining us watching today too, why don't you tell us in the comments what you're looking forward to in 2021, or maybe a place you're hoping to visit, some rocks you're hoping to see. What are you looking forward to? Since this is our final Rockin Pop-Up of 2020. So without further ado, let's go back in time to some ice ages. What do you say, guys?
Sounds great.
Sounds great.
Graham, before we jump in, where are we right now?
Oh, whoops. All right. So right now we are, as we all know, we're hanging out down here in Santa Cruz, where we have not really felt the iciest bits of ice ages. But looking over here, we're seeing some different sort of views of North America and Europe, and then a pretty familiar view of the bottom of the world. But Gavin, what's going on here? What's all this white?
This doesn't look like what a map looks like today, Graham. If we travel back in time around 25,000 years, the continent of North America is pretty much covered with ice. All of Canada is under miles of ice. And our homes, Wisconsin and Long Island, are also covered in ice. So the North American ice sheet exists. Also, what about this picture in the middle? That's Europe, right?
That is Europe, yeah. So the British Isles, Norway, a bunch of Central and Northern Europe are just covered by this huge blanket of ice. This is what we call the Fennoscandian ice sheet. And there are a few other sort of regional names for the different lobes of it. But yeah, much of Northern Europe also just covered by just a big block of ice.
Yeah, Graham. So again, this is what we're talking about today, the ice ages. So we're actually in an ice age, and the ice age itself is the last 2.5 million years, is the current ice age. And these ice sheets we're showing are one of the last really cold periods within that ice age. But Graham, is the 2.5 million years the first ice age in Earth's history?
No, certainly not. The Earth has a long history of having these really icy periods, times that are so much icier than our current ice age, where the entire Earth was engulfed in ice, or maybe even like almost down to the tropics. So these are called Snowball Earths, and we've talked about them a few times before, but these happened hundreds of millions of years ago to billions of years ago as the Earth went through these extreme changes in a lot of its like climate system and just got to these really, really, runaway cold conditions.
That's right, Graham. And so this is a really important point. The ice ages we see in the last couple of million years are not unique in Earth's history. We've had several ice ages, which you can see in this bottom left graph here. This is temperature versus time. And so you have large temperature fluctuations throughout Earth's several billion year history. But we're going to talk today specifically about the last 2.5 million, because we really know a lot about what happened in those ice ages and how temperature was fluctuating, how the ice sheets were fluctuating, and what caused all of that. So should we jump in, Graham?
Yeah, but just before we dive in, I think this is a good thing to mention that you talked about how we are in an ice age today. And yet some folks may say, well, gee whiz, geez, where's that big ice sheet over North America? And that's a very reasonable question. And that's because even within an ice age, you can see fluctuations, this variation in climate. And so in this figure down here, you can see how even over the last few 100,000 years, our ice age has been marked by relatively warm periods, like today, where a lot of the ice sheets have melted, and only a few of them are left behind. And then times where it's gotten way colder and these ice sheets have expanded, what we think of as our last glacial maximum or most recent glacial event. And so, Gavin, like you were saying, how do we even know that North America was covered with ice?
Graham, that was a really good point. Thanks for throwing that in there. And I really like this starting place. Like, how do we know just geologically, without all the fancy chemistry like we're going to get into in the rest of this pop-up? People have been studying ice ages, and people talked about ice ages starting in the late 1800s. So how did they know? They didn't have all the technology. Well, they were geologists, and they walked along the Earth's surface, and they saw these weird features that they thought must have been caused by glaciers, but they were in weird spots, Graham. And so we have a picture of that map here with the North American ice sheet, and this is a good place to look because we have glacial features in weird areas. And so this first picture to the right of that map is an area that's familiar to you. It's in the middle of our country, in Wisconsin, and it has these interesting sort of lateral parallel features. This is a aerial shot, so these are large hills. Graham, what's going on here?
Yeah, so like you said, we've got this this whole sort of sweeping line of these kind of long egg or teardrop shaped sort of hills on the ground. They've got these sort of blunt noses and then they taper out to the back. And these are called drumlins. These are these sort of glacial hills that form as a great big ice sheet flows over across a relatively flat area. It shapes all the sediment, the mud and the sand and the gravel around there into these sort of lumpy hills. And this is something that's forming deep under an ice sheet. So when these were forming, there was lots of ice up overhead. But that's not the only place where ice sheets are shaping the ground around them. Isn't that right, Gavin?
That's right, Graham. Had to throw a picture of Long Island here because Long Island is actually a glacial feature. Before 40,000 years, 40,000 years ago, Long Island did not exist. And that's because 40,000 years ago, the glacier, sort of the edge of the glacier reached where modern day Long Island is. And there was a mile of ice above it. This is a big ice sheet that's above here. And what it did was it started melting back. And when it melted, it dropped out all of the sediment that it was carrying. So as we've said in previous Rockin Pop-Ups, glaciers are really, really strong erosive forces. They erode out a bunch of bedrock and they create a bunch of glacial till, we call it, glacial sediments. And when they melt, they leave behind these sediments and these big features called moraines. And so Long Island is 2 glacial moraines, and that's why it has the 2 forks, because those are the remnants of the 2 glacial moraines that actually made it. And so, Graham, this is really interesting. We have these features that are in the middle of the continent. There's no ice anywhere near them. And so if you were a keen observer to the geology before we knew about ice ages, you would say, wow, there must have been a big ice sheet here, right?
Absolutely. Yeah. So these are a few of the ways. There's also some other cool things, some that might be a little bit more familiar to us. Us folks in California, if we've been to Yosemite and seen some of the glacial features there. So you don't see a ton of drumlins. You definitely see lots of moraines up there, these big mounds of gravel and sediment. But then there are also these really kind of interesting bedrock features that are made of solid rock called, oh my gosh, it's a French word and I just forgot it, Gavin. You know it, roches moutonnées.
That's right, Graham. You saved yourself. I think that's the coolest geology name of anything, any feature, a roche moutonné. So, Graham, what's a roche moutonné?
Yeah, so these are things that form not from sediment being piled up like a drumlin or a moraine, but these are formed when ice is scraping and grinding across the surface of rock. And so I mean like bedrock. I mean hard, solid rock on the ground that's fixed in place. And that glacier is just grinding it down, and it polishes the sort of smooth sloping surface to it, like you can see here. But then on the other side, it ends up kind of catching the edge of it. And so it'll peel off chunks of rock off of there and sort of take these large boulder-sized rocks and tear them off the sort of forward edge of that. So you get these sloped, shallow sloped fronts with these really steep, sort of precipitous, jagged cliffs on the other side.
That's right, Graham. And anybody who's gone to Yosemite, I know you mentioned Yosemite. Yosemite has some of the most world-class roche moutonnées. All of the domes near Tuolumne Meadows, for instance, are just these beautiful roche moutonnées, and that's why they're shaped the way they are. And Graham, I like that you have another feature here, because I think that for the easiest glacial feature to notice on the surface of the earth are these things called glacial erratics. And it's simply just a giant boulder that is placed in an area where it doesn't seem to fit. So I'm sure the audience can imagine what moves boulders in the modern day surface of the earth. Mostly rivers and sometimes, oceanic forces, but water, and that's pretty much it. But when you had huge ice sheets, you are plucking out big boulders and leaving them places. And so these past geologists must have seen these features and been like, man, a river couldn't have moved that. This is a big boulder and it's out of place. It must have been an ice sheet that moved this big boulder.
That's right. Yeah. And often in places where this ice sheet was all through the sort of northern plains, like you see these huge boulders out of nowhere, surrounded by sometimes farm fields, sometimes just prairie. And yeah, those are the calling card of a long gone ice sheet. But there are other ways that we can go back, and even ways we can less piecemeal go back and find out how the Earth's climate and how its ice cover has changed. Isn't that right, Gavin?
That's right, Graham. This is how modern day paleoclimatologists think about how climate has changed. And that is, we find records of the changing climate in areas throughout the earth. And so this is the first way we find one of these records, is that we actually drill into the ocean sediments and we find these layers. And these layers are sort of like pages in a book that are laid down throughout Earth's history. And they talk about, or they show what changes have happened in the climate. And so these drill cores that we have in the ocean, we've drilled in several areas in the ocean. So this bottom left image, all of these gray dots in the ocean are areas where we have deep drill cores. And so we're looking at these sediments, and we are making a global image of how the ocean has changed based on these sedimentary cores. Is that right, Graham?
Yeah, that's right. And so, yeah, by going to all these different points, we're able to make a more global picture of it. But then in each one of these cores, right, you're able to sort of get a glimpse of how things are changing here. And just by looking at them, you can see all these layers where it's alternating from different colors, different thicknesses of the layers. You know, you can even just get a sense that, right, things are changing around this part of the ocean. It has not stayed the same through time.
That's right. But Graham, is this the only area where, or the only way we have to look at past climate are these drill cores?
Not at all. These are some of the longest lasting ways, but there's another way that the climate actually records itself within the ice sheets that we often think about as changing with that climate. And so by drilling down into ice sheets, we can pull up these cores of ice, and those tell us something about how climate has been changing through time.
That's right, Graham. Yeah, as the climate changes above them, the ice sheet, the ice itself records these changes in climate. And just like throughout the ocean, we have ice cores all throughout Antarctica. And so we have ice in very deep cores. The longest of these ice cores are 3.5 kilometers long. And we can say things about the last 800,000 years of climate history with these ice cores. But Graham, we're telling folks at home that these pages of the book, of these books, these layers that we have in these climate records are changing with the climate. They're telling us something about the climate, but how does that work?
Yeah, so what folks are measuring in these are different sorts of elements, different isotopes of elements, so elements that weigh different amounts and are sort of wiggled around by the temperatures and how they change on Earth. But a really important thing here is that these are relating, both these changes in the ocean and these changes on the ice sheet, those are changing in response to how ice is growing or shrinking on the surface of the planet. And just as when ice shrinks, the ocean will shrink or grow in the opposite direction. So you can think about this as when we've got warm climates, we've got small melted down ice sheets, they've dumped all their water into the ocean. But then when you cool your climates down, and especially when you cool off your summers, you can start keeping ice around longer and these ice sheets will grow out and you'll start taking water that's out of the ocean, right? It rains down or snows down onto these ice sheets and it starts staying there and it never makes it back out to the ocean. And so our ocean levels will start to fall a little bit as we start storing water up in the ice sheet. And so as water goes in between these two places, it's actually going to change some of the chemistries of these different glacial ice or ocean sediment cores.
Ah, okay. And so the changing layers are actually are responding to the changes in the amount of ice in the ice sheets and the amount of water in the oceans. Is that what you're telling me?
Yeah, that's exactly it, Gavin. And so when we start looking through those, what do we start to see through time?
We start to see the response of the ice sheet. And so this is a really cool like fingerprint of an ice age, because as we know, in an ice age, the climate gets colder, which we can measure through the ice cores. We can measure actual climate signals, but also the ice sheet grows, and we can measure that through both the drill core record and the ice core record, the fact that we have more ice on the surface of the Earth.
Cool. Yeah. And so by reconstructing that, we're actually able to go through these sort of cycles and see how it varies through time. Oops. And so, yeah, we can use both these little critters that we pull out of ocean cores. We can also look to these variations in the ice. And a kind of a slick thing with the ice is that because ice is forming from snow, it's trapping bubbles in there. And so by looking at those bubbles, we can actually tell not only or by looking at the ice, we can tell how cold our climate was. And by looking at those bubbles, we can see what our atmosphere was like then. And so an important thing there is recognizing CO2 and other greenhouse gases. And we've been able to see that those things are following the climate. And the climate and the greenhouse gas budget are influencing one another through time.
Interesting,
sorry.
Graham. Okay.
But yes, I jumped ahead there, Gavin. But yeah, what's one of the things that really pops out about all these records?
Well, Graham, the fact that they're cyclic, right? They're sort of back and forth, right? You have periods of really warm periods, and then followed by periods of cold periods, but they're following a cycle, right? They're not just happening here and there. They go back and forth, back and forth. And we see that throughout the past 5 million years of Earth's history, right? So there must be something very systematic going on that's changing the climate, that's affecting the ice sheet and the oceans. What is that? What's changing, Graham?
Yeah, so what's been really important over the last couple million years, or a few million years, has been these variations in the Earth's own orbit. And so our Earth is spinning around on its orbit, but it's also doing some kind of funky things like a top. And a big one of them is this axial precession. So if you've ever spun a top and seen it start to slow down, you'll notice the top of it starts to wobble. Well, our planet has been doing that for millions and millions of years. And in this last ice age, our climate has been so sensitive that just these little wobbles of the Earth as it spins around has been causing these big changes in how much sunlight hits the Earth. And then also, because of how much sunlight, how warm or cold our summers are and how our ice sheets can grow or expand from that.
That's right, Graham. Yeah. So this axial precession, the spinning, as you said, affects the amount of energy the Earth gets from the sun over its summers. It affects the ability for Earth to grow ice sheets. And it actually just so happens that it takes 20,000 years to go through one revolution. So every 20,000 years, we're getting a differing amount of incoming energy from the sun. And that changes the climate, as you might imagine. But there's not just one thing about Earth's orbit that affects the climate. There's a few. And so the second really important one we talk about here is the tilt of the axis, right? So it's not, the Earth is both spinning like a top, but it's also sort of has an oblique tilt to it, right? And so it's just 2 degrees that shifts. And how long does this obliquity cycle go for, Graham?
Yeah, so this obliquity cycle is changing around like every 40,000 years. It'll go all the way, it'll lean its 2 degrees extra over and then come back. And so within 20,000 years, it'll lean forward. And then another 20,000 years later, it leans back a little bit more upright. And so we also see these sort of 40,000 year cycles of it getting a little bit chillier and a little bit warmer. But what's really key here, Gavin, is it's not always just the individual ones, right?
That's exactly right. And that's the reason why we put this graph here on the right. Paleoclimatologists have a pretty tough job because they have to try and decipher what about the Earth's orbit is changing and what exactly is driving the changes in the ice sheets. So it's a combination of several of these changes in Earth's orbit. So that's these 3 in this graph over to the right. That's these 3 separate features. You have the red is the precession, that's the 20,000 year cycle. Green is obliquity, that's the 40,000 year cycle. We have eccentricity, which we didn't talk about, but that's an even longer cycle. And so these, they basically combine with each other and they affect how the overall solar forcing is happening. And that in turn is what is causing the ice sheets. So it's a bit of a complicated story, but it all comes down to how the Earth's orbit is changing through time, and it's cyclic. So that's why you have these cycles of icy and then not icy.
All right. But now so if we're going by these cycles, and I'll actually just hop back here, right? As we're getting up closer to the present, we see these get kind of warm and then drop down and warm and then drop down. So we're kind of up at these warm peaks. So we should be cruising back down into another glacial period. But Gavin, that's not happening, is it?
That's right, Graham. And so one thing that people ask us paleoclimatologists is that, okay, we're in an interglacial, and we know that several times in Earth's history, we've seen the Earth get warmer. So how do we know that the global climate change that's happening now that scientists are sure is happening because of human induced features in the climate, how do we know that that's human induced and not just normal climate change like we see in the past? And this all comes down to greenhouse gases, Graham. And first of all, why do we call them greenhouse gases? Like, how does this work? Because this is a big question, right? Well, not a question, but it's an important distinction.
Yeah, so you can think about how greenhouse gases work just by thinking about how a greenhouse works. A greenhouse has windows on it that let sunlight in, but keep the heat inside of there. So they get warmed up by sunlight, but that glass helps to insulate the heat from going out. That thermal radiation gets caught up inside that greenhouse, and so it gets warm in there. And that's why they're great places to grow plants. But when your whole Earth starts having more greenhouse gases, these things let sunlight down onto the Earth, but they don't let the Earth cool off or release its heat very well. And so what happens is as our greenhouse gases go up, it's like we're getting thicker panes of glass on our greenhouse, and those help to keep it warmer down at the surface or inside of that greenhouse.
That's right, Graham. And so as you alluded to, the greenhouse gases, that CO2, that's the most important one that we look at. Those greenhouse gases have changed on those glacial interglacial cycles. But here's the kicker. Here's how we know that it's human induced and not just a normal CO2 variation. These are these really important curves here. This first one on the left is called the Keeling curve. And Graham, can you describe what this is actually showing? What are on the two axes here?
Yeah, so this Keeling curve, this shows the amount of carbon dioxide in the atmosphere, and then it's showing time here, and the font's a little small here, but it's starting in 1960, and it's going all the way up through 2020, because this is showing the long-term recording average. And this blue line shows the average for each year, but these red lines actually show this cool pattern where in the summers, the trees are all getting lots of sunlight. They're gobbling up carbon dioxide from the atmosphere, making sugar, doing their photosynthesis, and having a great time growing. And then when it cools off, sometimes they shed their leaves, and and all of that carbon kind of gets released as their leaves decay or as they just stop pulling it out of the atmosphere. So as the plants on Earth are getting more and less sun and are going through their seasons, they're actually kind of breathing in and breathing out CO2. So we get these wiggles every year, but once we zoom out from this, we actually see that there is a stark upward trend.
That's right, Graham. Yeah. And so something really cool that climatologists can do is figure out how much of this trend is affected by natural processes and how much of this trend is being affected by how much CO2 that humans are putting into the environment. So that's what we have this graph on the right-hand side. We have the amount of temperature change based on the amount of CO2 on the y-axis, and we have the year time on the x-axis going from 1850 to 2000. And the blue curve is all natural factors. So any natural factor that pumps CO2 into the environment. The black dots are the increase in temperature that we see. And the red curve is all human factors. So burning of fossil fuels, things that humans are doing to pump CO2 in the environment. And as you can see, the blue curve just doesn't keep up with the increased trend in temperature, whereas the red curve is a really nice fit. And so that's showing us that natural factors over this time period can't be what's causing the increase in temperature that we're seeing. But Graham, these are over very short time periods. This is the past 200 years or so. How does this change that humans are inducing compare to the CO2 cycles that we were talking about throughout the Pleistocene?
It's a big difference. When we look at this kind of zoomed up, it doesn't look like we've flown that far. It seems like it's going up, but what's the background? Well, we already were starting at a high CO2. CO2 always kind of comes up in an interglacial, these sort of warm periods between glacials. And so we were already in that period of really high CO2 for our Pleistocene Ice Age climate. But now we've actually gone way off of our normal pattern. We started out high and we just keep going higher by burning fossil fuels and releasing carbon dioxide. And so it's really taken off, and it will, take off, continue to take off unless we, make some big changes in terms of how we consume and use fossil fuels.
That's right, Graham. So this is a good stopping place, I think, because this is kind of why paleoclimatologists do what they do. They try to figure out what happened in the past in the past climate, so that we can figure out what's going to happen in the future and how humans are causing that. And so this is why there's such a big consensus among scientists that humans are causing climate change that's different from the past. It's because of these really, really stark factors that you just can't really argue with the numbers. So
that's right.
Okay, Graham, that's a little bleak, but it's a good place to stop for the paleoclimate. Let's do a shout out to our blog coming up.
That's right. So later this month, we'll be dropping our next installment of the Rock Record. And here we're going to spend some time sort of thinking about and taking you through our favorite outcrop in Santa Cruz, the Swift Street outcrop.
That's right, Graham, I'm looking forward to it. We've done a Rockin Pop-Up on this, but this will be a nice guide that people have that they can just access online. So if they're ever down on Swift Street and they want to see the cool rocks there and figure out what it all is, what it all means, how it got there, they can do that.
Yeah, looking forward to it.
I'm so excited for that one. That's we've talked about this a lot, but that's my favorite spot in all of Santa Cruz. So I'm excited to, next time I go visit it, have your guide in hand. So it'll be like I'm visiting it with the Geology Gents. It's gonna be great. Well, thank you for that, Gavin and Graham. I'm curious about a term you were using. So I've always thought of the two of you as geochronologists, and you've been using the term paleoclimatologists throughout today.
Right.
Could you just share what the distinction is between those two titles?
Yeah. Sorry to throw some jargon into that. Paleoclimatologists just is a term for people who study the climate in the past. And so those two things you said, geochronologists and paleoclimatologists, are not mutually exclusive. So geochronologists just means that me and Graham try to find out the age of rocks. That's our specialty. But we can really say anything with the age of rocks by knowing the age of rocks. So one of the things that we answer with the age of the rocks is how that sort of fits into the climate story in the past.
Got it. Okay, cool. Thank you. And I also just wanted to let everyone watching know about another kind of geologically inclined event that the museum's got going on. And that is with one of your sort of colleagues, I think maybe up at UC Santa Cruz, Noah Finnegan, who's a geomorphologist from the same department as Gavin and Graham. He's going to be giving a presentation for the museum next week on Tuesday at 7 p.m., Tuesday, December 8th. And he's going to be talking about fire and mud. So we actually had another one of your colleagues join us a couple of months ago to kind of talk about fire impact and on the landscape. And so we're going to have Noah Finnegan kind of elaborate on that too next week. So I'm going to put a link in the comments so that people can sign up to join us for that. And then one other link I wanted to share with you all, because like we started off today talking about, this is the last Rockin Pop-Up of 2020. Don't worry, there will be more. We're coming back at you in 2021. But we also want to make sure that that we're giving y'all what you want from us. So let us know what you think about the Rockin Pop-Up with this survey that I'm putting in the comments as well. So if you could be so kind and share your feedback with us, it'll just take a couple of minutes. We'd really appreciate that. And again, look for the Rock Record blog that will be coming out in a couple of weeks from Gavin and Graham. You can sign up for the museum's newsletter to be notified when that is ready. So without further ado, thank you so much, Gavin and Graham, for this final Rockin Pop-Up of 2020. And when we come back in 2021 in the new year, do we know what we're going to be talking about yet? What are you guys going to be presenting?
That's a good question. Graham, did we talk about this yet?
We did, yeah. So where we left it today, we're talking about, right, we spent this whole Rockin Pop-Up talking about how the climate changes. We finished talking about how our climate is changing very rapidly. And so next time, we're going to do a little bit more paleoclimatology. We're going to look back into some climates of the past and think a little bit more about what has happened in Earth's history when we change the climate suddenly. And spoiler alert, it involves mass extinctions usually. So we'll get a chance to sort of see what that has looked like over Earth history. And hopefully, yeah, learn a little bit more about how life and the climate has changed in really dramatic ways on Earth.
How fun. Wonderful. I know you guys were trying to end it on a high note and then we just brought it back down. That's okay. Sometimes that's how it goes. All right. Well, I'm really looking forward to that. And I hope you guys have a great month, and I'll see you in the new year.
See you in the new year.